That's okay, because I've had one computer for multiple years, so on average, Zoe, we're doing good.
Well, my first computer, it wouldn't charge with any code in the classroom, not even mine. The teacher's code, the power brick, nothing.
That's not a good thing. For a computer, it's bad when they don't charge.
No, it wouldn't power up, boot up, nothing with none of the codes.
Well, that happens. That's why they gave you a new one, right? That's why they gave you a new one. Jimena, no. You're asking the wrong person. It is possible, but it may not. I don't know.
It may not work. Really nice for you. Take this. Deal with this.
You know, I got to admit, for the longest time when I let you guys pick your seats, you all went to the same area. Now you're starting to move around. It's taking me longer to do attendance. I don't know if I like that.
I'm always in the same seat.
I understand that, Zoe. But some of you are moving around, you know, moving from the front to the back and things like that, which I guess is all right, but we'll figure it out as we go, ladies and gentlemen. So
you're going to get more confused.
Zoe, it is impossible for me to get more confused. It is possible for me to get confused again. So, but more confused, like nope, can't happen.
Yes.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect, perfect, perfect.
I will.
All right, ladies and gentlemen. All right. Please get logged in to joinpd.com. There's your code IPLBZF. Okay. Today we're going to talk about the last of our gas laws. Okay. We've got an activity that we're going to do, a worksheet that we're going to do tomorrow. We got a lab activity that we'll start on tomorrow. May take us into what? Did they knock?
Yes.
I never heard it. Sorry. Okay. So the lab activity will be tomorrow and part of Monday probably. And then Tuesday we will review. Wednesday we will be taking our test in here, just so that you are aware, ladies and gentlemen, covering gas laws. So that's what I got on the board here for next week, Wednesday. Thank you for those of you who turned in the Boyle's Law Lab yesterday. I did get them graded. I did hand them back to you, ladies and gentlemen. So that is done with you. I also got your worksheets graded and handed back to you, those of you who turned those in. So keep in mind, please keep up with the class. Victoria, what can I do for you?
Do you know what we're doing Thursday to Friday?
Of next week?
Yeah.
Yeah, you can come see me about it, and I can let you know. I have an idea, but we'll be starting the nuclear unit. That's what we'll be doing. So, okay. Anyway, ladies and gentlemen. All right. So, there's the code if you're just getting in for logging into the Pear Deck IPLBZF. Okay. Again, I want to stress to you, we have given you a bunch of gas laws. Today, we will put them all in one place for you. I will summarize them all for you. Okay. But on your test next week, you are going to be asked questions, not to calculate gas laws, but to predict what will happen if we make this change to a gas. So if we change the temperature, what will happen to the pressure? If we change the volume, what would happen to the pressure? If we change the temperature, what would happen to the volume? Okay? Those are the gas laws that we have been discussing, and we've talked about what the relationship is. So that is what a lot of your test will be on, ladies and gentlemen, just so that you are aware. So Boyle's law shows that pressure and volume are in what kind of relationship? Okay? So what kind of relationship are pressure and volume in? Choose one of the choices that you have there ladies and gentlemen? Okay, so we're about 50-50. Now we are 50-50, okay? Bad news for those of you who just changed that, you should have gone the other way, okay? Boyle's law is an inverse relationship, okay? Now what that means, if one variable goes up, the other goes down, okay? So again, on the test next week, I will give you a problem and I will say, all right, the volume of a gas goes up. What would happen to its pressure according to Boyle's law? You need to tell me that pressure would go down, okay? Why? Because that is the relationship. Again, I'm not asking you to do calculations. We take a lot of the math out of this class, but I am asking you to understand how one variable relates to another, and that is what the gas laws are all about, okay? In any direct relationship, the variables must be in what mathematical relationship? So we've shown you the formulas for all of our inverse and all of our direct relationships. What do we do to the variables in a direct relationship? So again, you've got some choices there. You can make your choice, ladies and gentlemen. Sorry, screen's too big to show you all of them. In a direct relationship, ladies and gentlemen.
I was stuck between two of them.
Whoa. That ain't right, is it?
No.
No. Should be division. Sorry.
Yes.
Should be division. Okay? I must have the wrong answer on that. Well, I have the wrong answer on that one. There's no question about that. When they are divided, that is a direct relationship, ladies and gentlemen. So division should be it. According to Boyle's law, if a piston makes the volume of a gas smaller, its pressure will do what? Now, you may not know, or you may know what a piston is, ladies and gentlemen. That doesn't matter in this problem. But if you were taking a test and you're like, Mr. Brand, I don't understand what you mean by a piston, I would come over and I would explain it to you. Okay? So think about the syringe that we used in the Boyle's law experiment. The syringe could move in and out inside a cylinder. That is basically what a piston is. A piston is a inside of a cylinder, and in your car's engine, that piston moves up and down and changes the volume inside that cylinder for the gases involved in there. So if we make the volume smaller, ladies and gentlemen, what's going to happen to the pressure? Pressure is going to get bigger. Pressure is going to increase. Okay? Again, that's that inverse relationship in Boyle's law. All right, last question, ladies and gentlemen. If a graph were made of Boyle's law relationship, the line would be doing what? So what would the line be doing? And specifically, I guess what I'm looking for is what direction is it going and what shape does it have? So in a Boyle's law, what direction is it going and what shape does it have originally before we did that little trick to it? So the first graph that we created, what would it look like? Bless you. Thank you.
My dad mad at me. I got him sick.
Huh?
Ethan sneezed and I was thinking to myself, my dad's mad at me.
Oh, because you got him sick?
Yep.
Okay.
That's what he texted me before school started.
All right. Well, at least half of you responded and gave it a shot, ladies and gentlemen. So, all right. First of all, the main thing is the line would be going down. Why? Because it is what kind of relationship? Inverse. Inverse means the line is going down. Now, technically in Boyle's law, I realized that we did a little trick to make the line go back up, to make it a constant relationship. But the original line we made went down. And actually, what shape did the original line have? Straight or curved?
Right.
The original line was curved going down. The original line was curved going down, ladies and gentlemen. Okay? Ethan.
So with Boyle's law, would it be going down and curved?
It would be going down and curved. In this case, the main thing is because of the relationship being inverse, you got to tell me the line is going down. That's what you have to tell me. The line is going down because it is inverse. If it is a direct, the line is going up. Okay? The line is going up. So we won't worry too much. I expect you to recognize a constant relationship in a line. But again, mainly I want you to know that, all right, if the line is going down, it is an inverse. If the line is going up, it is a direct. What would you do mathematically to the variables in Boyle's law?
Division.
Nope.
Or multiplication.
Yes, we would multiply these. P times V. Okay? All right. Good, ladies and gentlemen. Good. I will correct my bad answer in here eventually, ladies and gentlemen. So with that in mind, please open up your EISN, ladies and gentlemen, and get to this slide. This is what we were talking about yesterday with Avogadro's law. So if you would, please get to this slide, ladies and gentlemen.
I believe so.
Let me correct that one slide real quick so that I'm actually giving you the right answer. All right, excellent. Okay, so here we go, ladies and gentlemen. This is where we left off yesterday. Okay, we were talking about Avogadro's law. Avogadro's law relates volume and amount of gas, holds pressure and temperature constant. Basically, if you put more gas into something, the volume's going to get bigger. The volume's going to get bigger. This is assuming that you can change the volume. If you put more gas inside a container like a metal cylinder, you're not going to be able to change the volume of that. Okay? In that case, you're going to probably change something else. Okay? But if you can't change the volume, like with a balloon, the more gas you put in, the larger the balloon gets. Okay? Again, here's what it looks like, but we're not going to worry too much about doing the mathematics. Questions? Okay, so that takes care of all four gas laws. Now, there's one more gas law that I want to briefly discuss, then we'll summarize this and put it all in one place for you. That next gas law is what is called combined gas law. What do you think it does? Yes, sir.
I just got a question. Are like the gas laws, they're like the same regardless, they can't be changed?
Correct. That's what it means to be a law.
Okay.
In other words, if you're talking about pressure and volume, and those are the only two things you're changing, if volume goes up, pressure has to go down. Has to. Okay? If you're talking about Charles' law, volume divided by temperature, that is always the law. Meaning that if you cool a gas down, it's going to take up less space. Assuming those are the only two things you're changing. Assuming those are the only two things you're changing. Okay? Then you've got Gay-Lussac's law, pressure and temperature. Again, you slow a gas down, you lower its temperature, you're going to create less pressure. Those never change. Those are laws. Even Avogadro's, the more gas you put in, the more space it's going to take up. The problem is in the real world, you can't always just change one thing. You can't always say, I'm going to hold temperature and I'm going to hold amount of gas constant. In the real world, things change. The temperature outside today is different from the temperature yesterday. Okay? So, therefore, that has an effect on the air pressure around us. Okay? Also, you can change more than one thing at a time. It is possible to do that. We did that in the implosion lab. In the implosion lab, we didn't hold anything constant. Everything was able to move around. Okay? So That's another important point, and I will get into discussing that a little bit more as we go. Well, hello, sir. Combined gas law is more realistic. Combined gas law is more realistic because it allows us to change three things. It allows us to change pressure, volume, and temperature. Okay? Now we're still holding something constant. We're still going to hold the amount of gas constant. Why? Because normally when you talk about gases, you put them in some sort of container and you seal them up. Okay? That is the easiest way to do that with gases. Okay? A little what's filling the container? Air. Gases. Okay? Because this is open, you are filling this container. So now I take and I put a lid on it. Now I can easily change the temperature. How? I can hold this in a hot water bath. I could easily change the pressure. Squeeze it. Change the volume of this, right? Make it more or less. I can change those things about the gas inside of here. But the one thing that I can't change now is I can't change the amount of gas. Okay? So this is what we mean when we say it's fairly easy to put gases in something and to hold them. Now, here's the good news about combined gas laws, ladies and gentlemen. All the relationships that we just talked about, except for Avogadro's, still hold true here. In other words, pressure and volume are still in an inverse relationship. Pressure and temperature are still in a direct. Volume and temperature are still in a direct. But now you may be changing two things. Okay? And those two things both have an effect on the third. So we would have to look at how this one affects the third one and then how this one affects the third one. Okay? And that's what we're going to do. Okay. Yeah, we'll save that for a second from now. By the way, where has pressure and... Yes, go ahead, Faith. Right now, while we're getting into this? Sure, go ahead. You just missed the stuff. You missed the stuff. You'll figure it out later, I guess. If not, no. P times V over T equals K. We still have all of these things equaling a constant, some number that does not change. Okay? And again, as long as we do not change the amount of gas, this constant will not change. Okay? So, all we have done is combined all of the gas laws that we know. There is Charles' law. There is Boyle's law. There is Gay-Lussac's law. We've just put them all into one formula. Okay? So, we can also set one of these equal to another. Now, again, if I didn't make you do Boyle's law problems, I'm not going to make you do combined gas laws. But combined gas laws are a little bit trickier, and we will explain why as we go. Okay? We will explain why as we go. All right? Let's run this by you. It's a Friday night, right? You're sitting at home, and you get a phone call. And the phone call is from a good friend of yours, right? Somebody who you really like hanging out with, okay? And they say, hey, let's go do this tonight. And what they say, let's go do, you hate doing. You hate doing it. Going to the movies, going out to eat at this one restaurant, going, listen to this band, and you just hate doing this thing that your good friend says, let's do. So you're kind of like, well, let me think about it. 5 minutes later, you get a call from another friend, but not a real good friend. Matter of fact, someone who you really don't really even like very much. And they go, hey, let's go do this. And the problem is you really like doing that thing. You love doing that activity.
Well, are they paying for that activity?
It doesn't cost anything. It doesn't cost you anything. Okay?
More likely, because then
More than likely what?
going with that one friend that I don't like, because we can go our separate ways.
Well, during you're doing this thing, you're with them.
I mean, at the movie, you
No.
can like. if it's a
Okay,
movie-
but you're still going with them. So even if it's going to a movie, before the movie, they're sitting there talking to you. You're like, oh my God, why did I go? I don't like this person. But this was a movie you really wanted to see. So, what would have made your decision easier?
Doing it with a friend you like.
Doing it with the friend you like. If the friend you like says, let's do this, and it's something you really like, boom, no brainer, right? Versus the friend you don't like saying, let's do something you don't like. But the problem is you've got two different variables working with you, right? You've got the person and you've got the activity. And the person who you like doesn't want to do the activity that you like. So which one wins out for you, Victoria? Do you go do the activity you like with the person you don't, or do you do the activity you don't like with the person who you do?
I probably do, because
Do.
then I can talk.
Wait.
Which
Do
is
what?
you.
Like the
The
sex.
person.
Are you going to go with the person or are you going to go with the activity?
The person.
Okay. So that is a bigger force for you. You would rather be with someone you like rather than doing something you like. Okay, Kiana? Agree? Anyone otherwise? What?
I agree.
You agree? Okay. Point is, it's a harder decision, correct?
Correct.
Okay? If it were the person you like doing the activity you liked, it would be a no-brainer. Well, that's what sometimes happens with gas laws. Let me explain. This variable is changing and it tells the other one to go up. This variable is changing, should tell the other one to go down. Now, which way does that one go? And now it's not about, well, you know what, I kind of like this variable better than, no. It's a matter of which variable has a bigger effect on it. Okay? Which variable has a bigger effect? Now, if both variables say, you know what, you should go up, guess what that one is going to do? Go up. It doesn't have a choice, right? But if your variables, because now you've got two variables working against one, sometimes they're pushing you in the same direction, sometimes they're pushing you in opposite, okay? But again, I'm not going to ask you to figure out what the new variable is. I'm going to ask you to predict what would happen to it, okay? So, ladies and gentlemen, let's summarize all of this. Here it is, ladies and gentlemen. This is everything you need to know about all of the gas laws. We'll start with Boyle's law. It is the variables pressure and volume, the constants T and N. By the way, between these two boxes, we need to have all four variables, all four. And here is the relationship. Okay? Let me get this up here. You can copy this in. The only thing you may have a problem copying, did I put the last formulas in for you?
No.
Those you may have a problem copying then. Those you may have to leave blank. By the way, I've got combined gas law. It's on the next slide. So I just didn't have room on this slide for it. This summarizes everything, ladies and gentlemen.
So do we need another formulas for the test?
Um,
For the gas laws?
I would expect you to be able to recognize them if I gave them to you. I will not make you write them.
Ah.
Okay? So I will not make you write them.
So you won't answer a question like, what law is this with this formula?
No, but I may ask you which law involves changing volume and temperature. So again, you can know it by the variables, you can know it by the formula, either way.
Right.
Comma.
Just
I normally have to like go between them.
Yeah, I know, I do
to know
too.
which is which.
I'm getting better at it. Control comma puts the little numbers at the bottom.
Mr. Brand,
Ethan,
when you heard joke.
no. But go ahead. It better be clean.
It is clean. Did you know that trees poop?
They create waves, yes.
Well, if they didn't, we wouldn't have number 2 pencils.
Trees poop pencils?
Don't think too hard, Mr. Brand.
What?
Don't think too hard. Number 2 pencils.
I heard it.
Does a tree? What is poop?
Well, it's defecation, it's waste, it's
Number
things.
2.
Oh, that's not funny, Ethan.
That's why I said.
That's not funny, Ethan.
That was pretty funny.
Did you know I have a pet termite at home?
Really?
He wears a cowboy hat. I named him Clint Eatswood.
Well, that's a good one. That's it.
It's better than yours. And that ain't saying much.
I'm gonna retire from telling jokes.
Are you?
Yep.
Okay.
Never again.
You know, I used to hear jokes quite often. Now you don't hear them as much anymore. So, which is okay because the jokes that most people used to tell were very inappropriate.
Oh.
At least they would be considered so today.
So, Mr. Brand, for the last 3, how do you want us to copy those?
On the radio.
Oh. Here's how you could do that.
That'd be a good one.
Let's do a little zooming in here. Here's the way you could do them. In here, you could do this. You could do, which one am I on, by the way? I can't tell because I'm so,
The first
okay.
The,
So P divided by T. And again, if you want to put the ones in, 1, control comma 1, equals P 2 T 2.
You forgot to divide it.
Sorry, thank you. I forgot to put the divide sign in there. So that would be one way you could do it. Now, I need to make this a little bit smaller so that it fits. So that would be the way that you could type it in. Okay, that would be the way that you could type it in. So you could do it that way, and then that you could copy for these two as well. Okay, so I guess that would be the way I would do it. I thought in the past I had put them in there for you ahead of time, but apparently I didn't.
No. No.
Gentlemen, we okay there?
Yes, sir.
When you're done typing this in, if you would, please close your computer. All right. Victoria, please put your phone away. Thank you. Just so that I know when everybody's done.
It was funny for a minute.
So on the test, you won't make us do the temperature conversions.
I'm sorry, what was that?
You won't make us do like the temperature conversions, like.
Yes, I will make you do the temperature conversions. We did those on the quiz. I will make you do that
Like
calculation.
how we do like.
But what I'm not going to make you do is solve a gas law for volume given a change in pressure. I'm not going to make you solve a temperature for given a change in pressure. I expect you to know those things, but I do not expect you to have to use those on the test. Okay? I expect you to know the relationships. I don't expect you to know how to do the calculations.
Mr. Brand, do the letters have to be capitalized?
They are, because they are representing those things and we capitalize them. The only one we don't capitalize is N. So we capitalize P, we capitalize V. If you look in a science textbook, it will have P capitalized for pressure. It will have V capitalized for volume when they're talking about gas laws. Yes. Yes. Okay, so we're ready. All right. So, ladies and gentlemen, here's what I'm doing. This is combined gas law. But combined gas law is made up of Boyle's law. Combined gas law is also made up of Charles' law. And it is also made up of Gay-Lussac's law. Okay? So, here's the type of thing that I would give you, ladies and gentlemen. All right. So, we have a problem, and we are going to solve for volume. Okay? It tells us that you have a certain volume. It wants to know what a new volume is. So for us to do this problem, we need to know what happens to pressure. Somebody tell me, up or down, what happens to pressure? Mariana, pick one. Does pressure go up or down? Up. Okay. Also then, temperature changes. Does temperature go up or down, Faith?
If you're writing something, we can't see.
Did I freeze it again? Oh, I'm sorry. Sorry. I thought I had taken the freeze off. Temperature's doing what? Pick one, up or down? Down. Okay. So in a problem, if we look at it and our pressure is going up and our temperature is going down, what is that going to do to volume? Now, originally we would be able to predict these things because they would be in one of these three gas laws. So pressure and volume are related by Boyle's law here, correct? What kind of relationship is it? Inverse. So if pressure, ladies and gentlemen, is going up, what is that going to cause volume to do? Go down. So pressure is trying to cause this volume to go down. Okay, fine. Well, temperature, though, is also changing. And temperature is going down. What would that cause the volume to do according to Charles' law?
Go up.
No. These are in a direct relationship. That's what I mean. You got to understand the relationships. This is a direct relationship. So if volume goes, or temperature goes down, what would volume do?
Go down.
Volume would go down. So in this problem, what does volume have to do? Volume has to go down. That's the kind of question I would ask you. Volume has to go down because the two variables that are changing are telling it to both go down. This is your best friend asking you to do what you really like to do. No brainer. You're going to do it. Okay? You're going to do it. Okay? So that is what we are going to look at in these problems. All right. Pick a variable. Somebody pick one of the three variables. Alex, pick one. Pressure. So pressure is going to change. We don't know what it's going to do. Okay? So volume, up or down? Up or down, Lucy? Just pick one. Volume goes up. Okay? We know that volume is changing and going up. We'll show you a problem in a minute where you could figure this out. But basically, the volume goes from 2.5 liters to 6.3 liters. That means it's going up, right? Okay. So what is temperature going to do here? What's temperature going to do? Okay, let's say temperature goes down. Okay? So now we go into here and we look at pressure, but we look at it from both of these things individually. So if our volume goes up, what will that cause our pressure to do?
Go up.
Go down. Why? Inverse relationship. Pressure and volume are always in an inverse relationship. Okay? Always. Now, what kind of relationship are temperature and pressure in? They are in a direct. So if temperature goes down, what happens to pressure? It goes down as well. So what's got to happen here? It has to go down. As long as our two variables go in the same direction, or are forcing our unknown to go in the same direction, it has to go in that direction. It has to. Okay? It has to. All right, let's solve for something different this time. Okay? Let's solve for temperature. We know that temperature is changing. We don't know how. So when temperature changes, the pressure has to change and the volume has to change. Okay? What do we want the pressure to do here? Pick one. Pressure goes down. All right. Volume, I get to pick this time. Volume is going to go up. Now, people look at this and go, well, if pressure goes down, doesn't volume have to go up because of Boyle's law? No, because I am changing these two things. I am changing these two things. I could change them any way I want. Okay? Yes, if these were the only two things changing, then it becomes Boyle's law. But we have a third thing that can change here. So these could change in a direction they normally wouldn't. These could both increase. These could both decrease. That isn't Boyle's law, but that's how I'm changing these. Okay? And then we would figure out how temperature had to change to cause that. Okay? So now, pressure is going up. What is that going to cause temperature to do? I'm sorry. You said the right answer. I said the wrong thing. Pressure is going down here, which would cause temperature to go down. Yes, thank you. I'm sorry. I confused you. That is totally my bad. So pressure and temperature are in a direct relationship. Pressure goes down, that would mean temperature would be going down. Volume and temperature are in what kind of relationship? Okay, which means volume would cause the temperature to want to what? Go up. What's temperature going to do here? What?
Go up.
How do you know?
You don't know.
Then why is it going to go up?
Couldn't it do both because there is...
Well, ultimately, if something changes, it can only do one of two things, which is what? What? Go up or go down. I mean, we're talking about a temperature here. So it's 70 degrees in this room. If the temperature changes, what are the only two ways it can go?
Up or down.
Up or down. With all of these, we're talking about numbers. The only way they can change is to either increase or to decrease. That's it. Okay? They can't do anything else. They either increase or they decrease. Or they could stay the same. That is a possibility too. The point is, in this one, can we tell what's going to happen? No, you cannot tell. Why?
Because one's going up and one's going down.
Good. Because one variable is saying go up, the other one is saying go down. We can't tell what's going to happen. The only way we could tell would be to do the math. Do the math. Okay? We're not going to make you do that. We're not going to make you do that. So on questions like this, you're going to have answers like goes up, goes down, can't tell. We can't tell if the two variables are going in opposite directions. That is the only time we can't tell. If they're going in the same direction, we can. Okay? Questions? All right. Take and open up this worksheet, ladies and gentlemen, in Google Classroom. The Unit 6 Gas Law Review worksheet. Now, in a few minutes, you can fill in this top portion, which you've already done. And you can even answer the first question. But what I want you to do is get to number 2 right away, ladies and gentlemen. Let's get to number 2 because here is what you're going to do in this particular worksheet. Okay? All right. A flask containing 95.0 cubic centimeters of hydrogen was collected at a pressure of 731 millimeters of mercury. Okay, I need someone to help me here, and I need you to tell me that 95.0 cubic centimeters, what is that actually telling me? What is this number representing? Pressure, temperature, volume, or amount of gas?
Amount of gas.
No.
Volume on that.
Why volume? Because what?
The size of the container.
No.
It's measured in centimeters.
The unit tells you which one it is. This is a volume. Why? Volume is measured in milliliters, liters, centimeters cubed. Pressure ATM, mmHg, kPa, or psi. Temperature, degrees Celsius or Kelvin. Amount of gas, moles. Okay? So this is a volume. 731 mmHg, what is that? Pressure. 70.0 cubic centimeters, what is that? Volume. Temperature and amount of gas remain constant.
N.
So this is N, this is T, right? And those are not changing. Okay, so what variable is changing in the question? Which one do you know for sure is changing? Which one do you have two of?
Volume.
Volumes. What is volume doing? What? Volume is decreasing. Very good. Okay. What variable is it asking us to solve for? What? Nope. Listen. Variables. Volume, pressure, temperature, amount of gas. Which one of those four is it asking us to solve for when you read the problem? Pressure. Second sentence, the first three words. At what pressure? That is telling us that we are solving for pressure. So what variable are we solving for? We're solving for pressure. Okay? So which gas law do we need if we have volume changing and we're solving for pressure? Which gas law involves volume and pressure? Boyle's law. Boyle's law. Okay. So what's going to happen to pressure here?
It's gonna go up.
Why?
Less volume.
Because Boyle's law is inverse.
Both of you are correct. Because there is less volume and Boyle's law is inverse, pressure has to increase. Pressure has to increase. Now, again, I told you a long time ago, the important part of doing these problems is this over here. Recognizing what your number is telling you. What variable is it describing? Every number that we write in science has a unit. The unit tells you what you are describing. 212 doesn't mean anything. 212 is nothing. It is a number. 212 Kelvin now becomes a what? No, what does it become? 212 Kelvin. No. Which of those four does it become when I put the word Kelvin on the end?
Temperature.
Becomes a temperature. What if I say 212 milliliters?
Volume.
Now it becomes a volume. What if I say 212 moles? Amount of gas. What if I say 212 kPa?
Pressure.
That number can become any one of those four, but what makes it one of these four is the unit that you put on afterwards. So when you go through these things, you have to figure out, well, what is that number telling me? Is it telling me a pressure, a volume, a temperature, an amount of gas? Because now when I look at this and say, okay, I've got two V's, I know V is changing. How's it changing? Well, it's going from 95 down to 70. It's decreasing. Okay? It gives me a pressure. It asks me what the new pressure would be. That's what I'm solving for. Now I can figure out which law I need. Which law relates volume and pressure? Boyle's law does. What is the relationship? It's inverse, meaning I now know what direction this is going to have to go. Now, I would not make you do all of this on one question on a test. But I may give you this and give you the answers of pressure goes up, pressure goes down, temperature goes up, temperature goes down. What does it say about temperature here?
Nothing.
No, it does say something. What does it say about temperature in this problem?
It's the same concept.
It remains
So can
the
it go
same
up?
temperature. No.
Can it go down?
No.
So you could eliminate that answer. The amount of gas, does it go up? No. Does it go down? No, because it says it stays constant. Okay? It says it stays constant. Let's take a look at the next one, ladies and gentlemen. Okay, here we go again. Again, remember, pressure, temperature, volume, amount of gas. All right, here's a number, 560 milliliters. Here's a number, 120 degrees Celsius. Here's another number, 400 milliliters. Okay, important information. When I read this, it says assuming there is no change in pressure or amount of gas. Okay? And then, ladies and gentlemen, also, what would happen to temperature? Okay, those are the important things that when you read this statement, you should get. A gas occupies a volume of 560.0 milliliters. It's a number. We got to figure out what that number is. At a temperature of 120 degrees Celsius, again, another number. We have to figure out what it represents. If the volume is changed to 400.0 milliliters, again, another number. Now, what does it tell us this is? The volume. So if you read the problem, it may help you as well. Okay? But even without it telling me the volume it is, how do I know this is a volume? Because it's measured in milliliters. Because it's measured in milliliters, it has to be a volume, ladies and gentlemen. Okay? So again, there are multiple ways of letting things help you. This is a volume. This is a volume.
Isn't Celsius a volume?
No, what is Celsius?
Or temperature.
Celsius is a temperature. Thank you. Good. Celsius is a temperature. Okay, so if I've got two volumes, what variable do I know is changing?
Volume.
Volume. How's it changing? What?
It would be increased, wouldn't it?
You tell me. Look at the two numbers and you tell me which way it's going.
It's decreasing.
Well, it's going from 560 to 400.
It would be decreasing.
Very good. That would be decreasing. That would be decreasing. All right. What variable are you solving for here?
Temperature.
Yeah, it says what happens to the temperature here. It gave us a temperature. We're solving for temperature. All right. So volume and temperature. Which gas law?
Charles.
Charles. And then finally, ladies and gentlemen, what kind of relationship is there in Charles?
It's a direct.
Okay, so if the volume goes down, what has to happen to the temperature?
Let's go down.
Has to decrease as well. Okay, ladies and gentlemen, questions? Okay, now, again, filling out the top may be helpful because, again, it puts all of those relationships and things in here. Answering this one question, why must we do temperature calculations in the unit of Kelvin when doing gas law problems? By the way, how many times have I asked you that question? Too many. I guarantee there's going to be one more time, if you know what I mean. Good. On the test. Yes. Okay. And then, ladies and gentlemen, you've got about 3 or 4 more problems here. Finish those up. Okay. Finish those up. If you have questions, if you need help, I will be more than happy to come around and give you assistance.